Hi, so my name's Ben Reynwar. Last 4 years I've been working for a tiny company doing error correction IP cores that go in flash controllers. So I think my original title was Python as a language for generation and testing, which is fairly unspecific. So I changed it to something even less specific, which is approaches to generation and testing. Really what I'm going to do the first half, I'm just going to talk about the tools I've been using, or what I've the tools I'm using at the moment. It is constantly evolving in time as I decided what I'm doing at the moment isn't working very well and I change things. And then the second half, I'll pick one little utility that I've released as open source and just talk about that a little. So just big picture of the stuff we're using. So stuff we're using for doing the designs, stuff for testing, synthesis, placing them out, and then deployment actually is more part of testing because we just sell IP cores. We don't actually deploy stuff to FPGAs. The orange things are other people's open source tools. Blue are things that I've released, but realistically no one's using them except people at my company, which is 2 of us. And or 2 gateway engineers, and then the black things are closed source. And you can see we're using largely open source stuff, except for this quadrant over here. And so hopefully that stuff that people were talking about this morning goes well, and then in a few years that will become more colorful as well. So we chose VHDL as our language. That was right at the beginning. 4 years ago, we had a consultant just to give us some guidance at the beginning, and he was a VHDL guy, so we chose VHDL. We use a fair bit of Python with Ginger 2 templating. We're using a lot of FuseSoC for keeping track of dependencies and also helping with generation. So I'll just talk about this a bit more. So it proved pretty quickly, we discovered you have to generate. We wanted, like I was thinking at the beginning, okay, we can just use pure VHDL for everything, but we need. Our customers are going to be using Altera, Xilinx, ASIC. We have a bunch of different error correcting codes, so we're going to customize the code word size. We're going to be customizing the error rate. Even things like the message widths in our iterative decoder will change depending on what you want your trade-off between resource utilization and error correcting performance to be. And for different customers, you'll choose a different trade-off. So there's no way, if you want to use all the nice types in VHDL and you want your types to be parameterizable, you end up having to generate code just so you can have even if you're just generating some code that defines constants and things like that. So, I mean, the basic level was having to generate packages defining constants for things like message widths. Then for some things, like even if you just want a parameterized tree structure, I haven't found any way to do that just in VHDL without generating code. I mean, I guess there's a difference here between what VHDL is officially supported. I mean, what VHDL is in the latest VHDL standard, and then what we can rely on all of the tools supporting and all of our customers' tools supporting. So, like we can't rely on a recursive instantiation, which would be lovely for making a tree structure, so you end up having to generate it. Sometimes there's bits of code that you're writing again and again, and it's tedious to type them out, so you want some kind of preprocessor. And then often you need wrapper modules, where you want to wrap some kind of module up in something, and you want to generate that. You don't want to be writing that out. So we were using FuseSoC for taking care of the dependencies, just because we have a whole bunch of different architectures. They share a lot of the, modules, and when we generate a specific architecture, we want to make sure we just include all the correct modules. And FuseSoC's a really nice way of just taking care of that dependencies, so when we generate a particular architecture, we're only going to pull in all of the VHDL files that we need for that one. But also, so recently, FuseSoC's also been extended for adding support to generate files. So this means that in FuseSoC, you can tell it what functions or what scripts to run to generate your packages of constants, your wrapping modules, and things like that. Unfortunately, that didn't exist when we started using it, so we have a little FuseSoC generators package that we're using at the moment, and I'm just starting to try and transition most of our stuff over to using plain FuseSoC. But we're still going to keep using this FuseSoC generators for a bit of stuff, because there we can, sometimes it's, like let's say you've got a design for ASIC, and you've got 10 different compiled memories in there, and they're all going to have different widths and depths. And you want to generate some power numbers for a bunch of different parameterizations. You don't want to manually have to go through the memory compiler and generate all these different memories of these different widths or depths. So what you want is some way to have a generating function that gets past all of the generic parameters that this module gets instantiated with. So let's say we've got our design with 10 different compiled memories. The generating function will get called with a parameter that's a list of 10 pairs of widths and depths. Then it can call the appropriate memory compiler, generate all your memories, and you can run your synthesis to get some power estimates. So that pretty much covers everything we're doing on the design side. On the test side, so we're using Python to write the tests, but we're not doing anything quite as clever as CocoaTB. So I guess we've got three kinds of tests. First of all, we've got the unit tests. So that's basically just Python interacting with a simulator through a file-based test bench. So we use GitLab just to run the automated tests. We're using VUnit. VUnit's a really nice framework for gathering up VHDL tests. But it's also written in Python and has Python pre-hooks and post-hooks for each test. So you can kind of abuse it by hooking in a pre-hook that generates your input file, hooking on a post-hook that analyzes your output file. So as long as you can deal with having your Python tests not be interactive, so the inputs don't depend on the outputs, then you can make it work. Then we're using VHDL for the simulations. slvcodec is a package that we have to generate these file-based test benches. And then axilent is another package just to, it's kind of like a PyNQ where if you have like an axi4-like interface, you can have Python functions and it relates those to the sequence of memory mapped commands. So you can easily just write Python, but it'd be doing the axi memory mapped interactions in the background. So then we have top-level synthesizable tests running on the FPGAs. There's no way we can test. It would be really, really slow to test our full big error-correcting cores in a simulator. So what we do is in the simulator, we'll test it on a tiny little error-correcting core. And then when we've got the full ones, we'll run it on the FPGA. On the FPGA, we're not only testing the hardware, we're also testing our error-correcting codes, because we want to be able to show that we only have one error every 10 to the 12 code words, and there's no way you're ever going to do that in a simulator or in software. You have to do it on the FPGA. So while we're testing that on the FPGA, we might as well be testing the hardware. So we have the error-correcting codes wrapped in a bunch of synthesizable tests, which expose axi4-like interfaces, and then the Python script can be running on the host and basically messing with that wrapper to try and mess up our hardware by stuttering the streams and things like that to make sure that when we're testing the code, we're also testing the hardware. And then finally, we have UVM tests, which they're not really like tests, they're more like documentation to deliver to the customer. Okay, so second half, I'll just talk a bit about slvcodec. So one of the pains with VHDL is that you always want to be converting things to and from standard logic vectors, but there's no default way of doing that. Because if you want to make a FIFO, you can't have a generic type going in as your data, so you convert things into standard logic vector. Let's say we've got a VHDL type here. We're defining a type for a complex number. So we've got a real part and an imaginary part, and that's some fixed width signed number. And in a real example, we'd probably generate this file and put in some arbitrary number there. And then we've got a type, which is an array of these complex numbers. So what slvcodec will do is it'll just pass this file. I stole the VUnit VHDL passing code and modified it a bit. And then that'll generate, this is just the top of the file, something like this, where it's just going to define a whole bunch of these to slvcodec and from slvcodec, and all these mappings of these your VHDL type to standard logic vector. So that way you can just run this over all the packages and just automatically have all these conversion functions. Then once you've done this, you're kind of halfway to being able to generate test benches. So what we want to do is for a given entity, we want to be able to generate a test bench that reads all its input stimuluses from a file and writes all the outputs to another file. So let's say we've got a module here. This is a complex, basically just taking that a complex number, and it's going to output a magnitude squared of that complex number. So all we're doing, squaring the real part, squaring the imaginary part, adding them up, and then scaling them down appropriately. So slvcodec will, again, pass this file to get the input and output ports, and it'll generate a test bench. I'm just showing the top here, but this is a VUnit test bench. It's defining a couple of types for the input, a type for the input port, a type for the output port. Then down here, there's some stuff to do with reading and writing the files and feeding stuff into to the DUT. So now we've generated a VHDL test bench. We also want to use Python to write that input file and analyze the output file. So a test, all a test is it's a class with two methods. One is make input data, and this is just returning a list of dictionaries, where here we've only got one input port, so each dictionary just contains one entry, I, and that's a dictionary here with a real component, an imaginary component, and we're just generating both of those randomly. It's simple because there's no interaction from the input and output. And that means there's some things that get more difficult, but for a simple just data streaming case like this, it makes things really simple. So then the check output data gets access to the input data, the output data. Here we're just grabbing all the input data and converting it to Python complex numbers, getting the mag squared, then getting the outputs that we got from the simulation, calculating the differences between what we see with Python and what we got from the simulation, working out what the allowable error should be based on a fixed width, and then just confirming that what we're actually seeing is always less than that allowable error. Then this is just a little Python script that is basically saying what the files are, basically just passing stuff to VUnit, so VUnit knows what Python tests to do, what the top level entity is, things like that. Once you've written this, I mean, in a real project, most of this you're only going to write once, or you'll be. This is just a simple example, but most of it you can kind of abstract out in a real project and not have to write it again and again and again. So the pro is, you don't need VHPI or VPI on the simulator. I mean, the con is the inputs can't depend on the outputs, and that's a really big con. I think in this case, the cons probably outweigh the pros, and if I was going to go back and go again, I'd just use CocoaDB, but it's kind of cool, and I will, even if I end up going back to CocoaDB, I'll still use the conversion functions to get those to standard logic vectors and from standard logic vectors. Oh, and then I think if I was going to go back here again, so you end up doing so much generation, I think you might as well just use something like MyGen or Chisel or Spinal, because it's really kind of silly ending up running templates for VHDL. I think it's kind of silly trying to do it in VHDL in the first place on hindsight. But I think that's about it.
Thank you very much. Questions? Yes, Jake.
So one of the really nice properties of your inputs not being able to depend on your outputs is you can do the FPGA-based testing. So if you were to use something like CocoaDB, how would you approach still using FPGA emulation for running all those tests?
Okay, so let me go back to my tests. I don't run all of my unit tests on the FPGA. I have the top level tests where I've got I'll have my encoder and decoder and some channel corrupting the data and then random number generator generate the data going in. All of that stuff I'll run on the FPGA. All the unit tests I could, but they're small. It's not really worth the hassle. The top level tests would actually be nicer if I was running on, so basically what this axilent is, that package is this Python level of abstracting out this kind of memory mapped interface to give it a kind of Python, let's see, I might even have an extra slide here. Oh, there, to give it a Python interface. So this is kind of an example class where this is a adder where you write to register A, you write to register B, you read from register C, and you've got the sum. And so this is kind of giving a Python interface to it where it's defining, this one's actually better. This is basically defining a command. So a command to add numbers contains a command to write to A, write to B, and then read from C. So then with that, I can use this interface both on the test bench and on the when I'm talking to the FPGA. And that would work just as well if I was using, I could switch out CocoaDB, and this would work just as well. Even all my existing tests, if I switched out to CocoaDB with the write inputs and check outputs, I could still have that on top of CocoaDB. It would just be kind of unnecessary. Yeah.
Okay.
Oh, sorry.
Oh. Okay, short.
Hello, hello. Hello. Okay. One of the really cool things in Python is Jupyter notebooks. Have you looked at integrating any of your things with Jupyter notebooks?
I used it for a demo at a industry thing. I had so basically my error testing, basically the tests I run on the FPGA, I put them on a board, then had a Jupyter notebook, and then was running basically could have the code, the Python code in the Jupyter notebook, and when you ran it, you could see the error correction performance and the throughput of the cores come up on the Jupyter notebook in real time. So you could just press go, and then you see like the gigabits per second as a function of the number of errors as a channel. So I mean, yeah, it's really nice for at least displaying it to other people, if not for actually running the tests.
Back to your FPGA's testing. I don't know how long your tests take to run through on the FPGA. Are they long, or are they?
I like multiple FPGAs for weeks. But because of the code, I mean, I need I could run them. The longer I could run them, the better it would be.
Right. Okay. The reason I was asking is the fact that back in a long time ago, in a company far, far away, I was responsible for actually testing a GPU on a vast array of FPGAs, and we actually were able to get through the whole test set in about 12 hours, when it should have taken about 3 weeks, stuff like that. So I was just interested in how long that. Yeah, thank you so much. That sounds interesting. Thank you.
Tim.
So it seems like you've looked at a lot of different Python stuff. If you wanted something, like frequently you want to create these wrappers, do you have any good suggestions for things that are able to pass existing Verilog and creating a wrapper based around existing Verilog or VHDL? Because there's lots of projects, but they all seem to fail in some different way.
Yeah, I mean, if I were to do it, I'd just use the VHDL passing from VUnit and just generate the wrapper from that. I mean, it's not. I guess I haven't seen like there's not one project I've seen that I would recommend. I'd probably just do it myself. But I guess that's the problem. Everyone's doing that.
You are using Questa?
Oh, that's just for our. I mean, we use Questa when we're having a particularly nasty bug and we want to. I just find the GUI a bit nicer than using GTK Wave. So sometimes we'll use it. And also for the UVM tests, we can't use GHDL. And our customers demand UVM tests, even if they don't demand that they're really testing it thoroughly. I mean, our interface is really simple. We're just streaming in a code word and streaming out a code word. So there's only so much you can do with a UVM test.
So you write assertions?
No, that's on my list of things that would be nice to do after this conference.
Okay. Then let's thank the speaker again. Thank you.